right, welcome. So, we're going to be talking about reasoning and logics. We're talking about reasoning and logics, and just as the name suggests, reasoning. What comes to your mind when you hear of reasoning? All right, something that makes sense, right? Logics, right? Things that follow a sequence, right? It has a flow, it has a pattern, and it makes sense. All right, so now in mathematics, the first topic in pure mathematics, Unit 1, is reasoning and logics. And reasoning and logics, it's just the study of statements that are true or false. So here I have the definition, right? It says that reasoning is concerned with the study of the truth or fallacy of declarative statements, which are called propositions. Now, that's all we're doing for reasoning and logic. So we're going to be looking at declarative statements, and we would have learned from primary school what are declarative statements, right? So in mathematical terms, declarative statements are statements that are either true or false. So any statement that I give you and you can determine whether it's true or false, it is said to be a declarative statement. So for example, let's say I ask you a question. I say, are you going to school tomorrow? That's not a declarative statement, that is a question. And since it's a question, then that is not a declarative statement, right? Now, if I tell you that I am 6 feet tall, I am 6 feet tall. Now, I am 6 feet tall, it's either true or false. We can prove it if I stand and someone measure my height, and then it's either I'm telling a lie or I am talking the truth. All right? And so that would be a declarative statement. I am declaring to you that I am 6 feet tall, and that is up to you or that is up to me and you to verify the truth of that statement. And the truth of that statement, when we study the truth or the fallacy of that statement, we call this reasoning and logics, which is a very important topic. So now we said that these declarative statements, we consider them to be propositions, all right? So we consider them to be propositions, and a proposition which is true, we give it a truth value of T, and a proposition which is false, we give it a truth value of F. T for true, F for false. Now, if you're using binary coding digits, sometimes you'll see 1 to represent true and 0 to represent false. So here we have some examples. It said the door is open. The door is open is a proposition. So if I look behind me, is the door, I can look and is the door open? I look at it and I say, yeah, the door open, or I can say, yeah, the door closed. So that statement is either true or false. The door is open. Now, is the door open? That is not a declarative statement. And since it's not a declarative statement, it is not a proposition. Now, if I say, go and open the door, or open the door, now that's not a declarative statement, that's a command. All right, and so commands and questions are not declarative statements. Commands and questions, not declarative statements. All right, so far we've just looked at the definition of declarative statements and propositions. All right, now let's look at symbolic propositions. Symbolic proposition now. So symbolic, as you know, in mathematics, we always use symbols. So for addition, we use plus sign. Subtraction, we have minus sign. Multiplication, division. We use symbols to represent operations, right, in mathematics. And so likewise, we're going to be using symbols to represent propositions, and these symbols are called variables. Generally, the symbols that we use are the letters P, Q, R, and S, right? Now, the first proposition, we usually give it the variable P. The second proposition, we give it the variable Q. The third proposition, the variable R. The fourth proposition, the variable S. Now, for Cape Maths, in specific, you only get a question with up to 4 variables, so you won't say any more than that. So 4 variables, P, Q, R, and S. All right. Now, several propositions, when you combine them together, you get what is known as a compound proposition when you put them together. All right, a compound proposition. So let's just think of an example. For example, I say let P, let P be, let P the proposition be I am 6 feet tall. P is a proposition I am 6 feet tall, and Q be the proposition. Let's say Q be the proposition I am a male, and R be the proposition and I am a teacher. So a compound proposition would be I am a male and I am a teacher and I am 6 feet tall. Now that is a combined or a compound proposition. All right, where we can just use the letter P to represent I am a male, Q to represent I am 6 feet tall, and R to represent I am a teacher. All right, that's all there is to it. So let's look at the example right here. Example, well, this is a different example. Example, let P be the sun is shining, Q be the rain is falling, R be the wind is blowing. So an example of a combined proposition right here, it is sunny and raining, but there is no wind. All right, so this proposition is combined, where P is the sun is shining, Q is the rain is falling, R is the wind is blowing. So notice that we combined more than one proposition. All right, we combined more than one proposition. And what we use to combine these propositions is what is known as connectives. So connectives are what we use to combine proposition. So we use connectives to combine proposition, and the main connectives that we use at Cape Mathematics are add, and, or, and, not. And, or, and not. Those are the three basic connectives that we use to combine simple proposition to form compound proposition. And so right here where we see it is sunny and raining. So and, that's the first connective that we use. Now this but is the same as not or nor. All right, and there is no wind. All right, so this is just some of the connectives that we use to combine this proposition. So the next thing we're going to look at is truth table before we get into connectives. And there's a reason why we look at truth table before we look at connectives. All right, now what is a truth table? A truth table is just a table that shows us all the possibilities of our propositional statement. All right, it shows us all the possibilities of our propositional statement. All right, so for example, it says right here, for example, right here, so consider we have one variable, right? Let's just say it is sunny. P represents it is sunny, right? Now that statement can only have two possibilities, right? So it is sunny. It's either it's sunny, yes or no. And so right here, we have, look at the first one where it says we have one variable P. The results that we can get from that is either P, which we say is it is sunny. Then the result is either it is true. Is the statement true? Is it sunny? Yes, then that's true. Now, is it not sunny? All right, let's say the sun is not shining, then my statement would be false. And so there are only two possibility. There are only two possibility when we use one variable. All right. So whenever there's one proposition, there's only two possibility. Now let's say there is two variables, P and Q, where P is it is sunny and Q represents, let's say, it is raining. All right. So it can be sunny and it can be raining. All right. So that's one possibility. Now it can be sunny and it is not raining. So that's a second possibility. Now it may not be sunny, but it is raining. So that's a third possibility. And the fourth possibility is it can just not be sunny and it is also not raining. So there are four possibilities for when we have two propositions. So what we notice is that the result is 2 squared, which is 4. It gives us 4 possibilities. When it was one variable, the result is 2 to the 1, which is 2 possibilities. All right. Now when it is 3 variables, it is 2q, which is 8 possibility. All 3 of them can be true, or the first 2 is true and the third one is false, or the first and the third one is true, but the second one is false, and so forth. And so we've deduced that the formula for when there's n variable is 2 to the n possibilities. So there's 2 to the n possibilities, right, when there is n variables. And so we use a truth table to determine the truthfulness of some statements, and the truth table never lies. The truth table always gives us the truth, and that's why we use truth tables. So if you listen to my words, I say, I said the sun is hot, right? That's my statement. Or I said the sky is blue. All right. The truth table will give you the result of that and tell you if that is true or false. Now I can tell you anything I want to tell you, but the truth table never lies. So that's why we use truth table. All right. So the next thing we're going to be looking at now is the connectives. And the reason why we look at the truth table first is because we're going to look at the truth table for the various connectives. All right. So let's look at the connectives. So the connectives, as we said, these are just operations, right, that we use to combine 2 or more propositions. And I told you the main ones that we focus on at CATE is and, or, and not. The sign for and is a sign that looks like to the raised to the power. It looks like the raised to the power symbol. So that's what we use for and. Right here it says and is used to form the conjunction, and the symbol is this weird symbol. Right, so it's the raised to the power symbol. So for example, P and the Q, that is P and Q right here. P and the Q. All right, or is used to form disjunction. So it's P or Q, and the or symbol is the almost looking like the for all sign. So this is the or symbol, a V. Some people call it a V, right? So if you want to call it a V is the or symbol. All right. And then the not. The not is a symbol that this is the not symbol called tilde. So we call this symbol tilde. And so tilde P really means not P. All right. And these are the basic operators that we'll be using to combine propositions. All right. So these are the basic connectives that we'll be using. So let's have a more detailed look at and. So the conjunction and, which is P and the Q. P and the Q. So if P and Q are true, then P and Q is true. Otherwise, P and Q is false. Think about it. So here's an example. It says the sun is shining for P and Q is the rain is falling. All right. So if the sun is shining and the rain is falling, that's the only way the statement the sun is shining and the rain is falling is going to be true. Think about it. P is the sun is shining and Q is the rain is falling. Now, if the sun is shining and the rain is falling, that's the only time that statement will be true. And so the only time P and Q are true is when both P is true and Q is true, then P and Q is true. Otherwise, it is false. So if the sun is shining and the rain is not falling, then P and Q is not true. If the sun is not shining but the rain is falling, then P and Q is not true because both of them still don't occur. And then now if the sun is not shining and the rain is not falling, then definitely the statement has to be false. All right. So that is the only time when P and Q is true. P and Q is true only when both P and Q are true. All right. Now disjunction. The disjunction P or Q. All right. So P or Q is going to be true when either P is true or Q is true. So if P represents the statement the sun is shining and Q represents the statement the rain is falling. So think about it. If I tell you something, right, I give you an or condition, any one of those criteria satisfies, then overall the statement is going to be true. So here we have P is the sun is shining and Q is the rain is falling. And so the sun is shining or the rain is falling. So if the sun is shining, which is true for P, and the rain is falling, which is true for Q, then P or Q must be true. Now, if the sun is shining but the rain is not falling, it is also going to be true. And if the sun is not shining but the rain is falling, or the rain is falling, or the rain is not falling but the sun is shining, then P or Q is also going to be true. And so the only time it is false is when neither condition happen. So the sun is not shining and the rain is not falling. So none of the criteria was met. And so that's the only time it is false. All right, and this is the truth table for P or Q. Now negation. The negation means not. So if P is true, if P is true, if P is true, then not P is false. If P is false, then not P is true. So for example, that's all negation really is, right? You're just turning it into the opposite of the statement. All right, so in English language, we would call them what? I think our, well, antonyms, synonyms, something of that sort, right? So just write the opposite of the statement, but in mathematics, we call it negation. So if P represents the sun is shining, then not P is the sun is not shining, right? If Q represents the rain is falling, then not Q is the rain is not falling. All right, so let's look at the truth table for this right here. So what we do the truth table for this is, the truth table for the negation would be, we have P, then we have Q, then we would have not P, and then we would have not Q. Now there are only two possibilities for P, and there are only two possibilities for Q. So the possibilities for P is going to be either true or false. And so the negation of P would be false or true, because the negation of true is false and the negation of false is true. Right? That's just the opposite. Likewise for Q can do the same. So we have true and we have false, and the negation of true is false and the negation of false is true. And so this would be the truth table of the negation. All right? Simple as that, very easy. All right. Now let's look at complex or compound proposition. All right. And so we're using again connectives to combine these propositions. And so a complex proposition is one which includes multiple simple propositions. Simple proposition is just a proposition, it's just one solitary proposition, like let P be, it is raining, that's a simple proposition. Q is the sun is shining, that's a simple proposition. But we combine these two, now we get a complex proposition. We're going to combine them using and, or, or not. All right. Now, if you do physics, you learn about many different kinds of gates, right, which are similar to truth tables. So in physics, you learn about the NOR gate, the inclusive or the exclusive or all of these stuff. But for Cape Maths, we only focus on these three: and, or, not. Only these three we're focusing on. Only these three connectives. All right. And so let's look at now a complex proposition. So here it tells us how to set up a complex proposition. So for example, it says the sun is shining and Q is the rain is falling. And now it wants us to write down the negation of P and not Q. So P and not Q. So P represents the sun is shining, Q represents the rain is falling. All right, and so P and the not Q is going to be the sun is shining and the rain is not falling. But then we need the negation of that entire statement. And so it is really reading, it is not the case that the sun is shining and it is not raining. All right, so it is not the case. All right, so inside the bracket represents the sun is shining and it is not raining. And so it is not the case that the sun is shining and it is not raining. That's how you would read that complex proposition. Now let's say we were asked to find the truth table of this complex proposition. Let's do that. So there are many stuff we'd have to write down. So we would need P, we would need Q, all right? Then we would need not Q. Looking at it, we need not Q. So how do I know what we need to form the truth table? I'm looking at what we have right here, what we're going to find the truth table value for. So we have P, we have Q, we have not Q, then we have P and the not Q, then we have the negation of P and the not Q. So that's how you determine all of which that you need to put in your truth table. So we have not Q, then we're going to need P and not Q. Then we're going to need the negation of P and the not Q. Negation of P and the not Q. P and not Q. So these are all that we need. There's going to be 2 to the n, where n is the number of variables. The number of variables we have right here is 2. And how do I know how many number of variables we have? Now, not Q and Q, that's still just one variable. P and not P, that's still just one variable. Not P just represents the opposite result of what is P. All right, and so not P and P is still just one variable. It's not a different proposition. It's the same proposition, but the negation of that proposition. All right, and so in this case, the number of truth values should have is 4 because we have 2 variables, P and Q. So now we're going to write, since it's 4 variables, this is how you write down what should be inside P and Q. You write true, true, then you write false, false. All right, some people like to start with false, false, then true, true. So let's write that down, true, true, false, false. Then you split the number of truths that you have here. So you're going to put for Q, one true, then one false, then one true, then one false. By doing that, this gives us all of the covered, this covers all of the following criteria. It covers when both P and Q are true, it covers when both P and Q are false, and it covers when either of them are true and false. Alright, so that's how you write down P and Q. Now, not Q is going to be the negation of what's in this column right here. So the negation of true is false, and the negation of false is true. Then the negation of true is false, and the negation of false is true. Now the next thing we need is P and not Q. P and not Q. So what is P and not Q? P and not Q, well, right here. So we're going to look at P and not Q. We're going to look at these two columns. So true and false. Now I need both conditions to be true in order for it to be true. And so true and false is false. And then true and true is true. Then false and false is false. And then false and true is false. The only time it is true is when both of the conditions are true, which is right here. True and true. Alright. So now the negation of P and the not Q is just the negation of this column. So we're negating this column, which then becomes true, false, true, then true. And that would be the truth table for this complex proposition that we have. Easy. Now, the next thing that we're going to look at is logical equivalence. Alright? Now, logical equivalence, it just means that two statements are pretty much identical. Alright? Two statements are identical. So two statements are identical. Two statements are identical, and the only way that these two statements are going to be identical is if they have the same truth value. Alright? So for example, if I say I have a red car, so my vehicle is red. If I say my vehicle is red, and I can rephrase that, right? So I don't know what's the term we'd say in English language, right? Construction, shift, or something of that sort. We could reword our statement so that it has the exact same meaning. In mathematical terms, what we're saying is that both statements have the same truth value. They're both the same statements, and so both proposition P1 and P2 are true. So here is an example. It says, show that the negation of P and Q is logically equivalent to not P or not Q. So the only way that we can show that the negation of P and Q is logically equivalent to the negation of P or not Q, the only way we can show this right now is using the truth table. And so they are logically equivalent if they have the same truth values in their truth table. Easy stuff. So let's show that these two statements are logically equivalent. All right? So I'm going to draw the table first. Let's draw a nice table. To represent P and Q. So that part is for P. This part is for Q. Then we're going to need, clearly from right here, we're going to need not P. Then we're going to need not Q. Then we're going to need P and Q. Then we're going to need the negation of P and Q, which is for over here. Let's just split it up some more here. All right. So this should complete the table. So let's type now. So we have P right here. Then we have Q. Then we have not P. Then we have not Q. Then we're going to have P and the Q. P and the Q. Then we're going to have the negation of P and the Q. And then we're going to have the negation, the not P or not Q. So actually didn't need this column right here. So let's take this part off. All right, so again, what we're going to have is for P, we're going to have true, 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 false, false. And why? Because we have two variables, so it's four possibility. All right, four possibility in each column. All right, and so true, false, true, false. Then we have not P. What is not P? Not P is going to be the negation of P. The negation of true is false. The negation of true is false. The negation of false is true. And the negation of false is true. Then we're going to have the negation of Q. The negation of Q is the negation of true, which is false. And then the negation of false, which is true. Then the negation of true is false. And the negation of false is true. Now P and Q. P and Q. P and Q is P and Q. Now P and Q is only true when both conditions are true. So here what we have is true and true. That's the only time it's going to be true. Everywhere else the statement is false. Everywhere else the statement is false. So now look at this now. P and Q. P and Q. The negation of P and Q, well, the negation of true is false. And then the negation of false is true. The negation of false is true. And the negation of false is true. So now the next thing that we're going to look at is right here. It says the negation of P or not Q. So not P or not Q. Not P or not Q. So what we're looking at is these two right here. So we're looking at not P or not Q. And so false or false is just false. And so false or true is true. True or false is true. And true or true is always true. Now, how do we know if these two statements are logically equivalent? We're going to look right here at these two columns. Now, since P1 right here, the truth result of P1 is the same as the truth result for P2, then hence we can say that P1 and P2 are logically equivalent. So that is, the negation of P and Q is logically equivalent to not P or not Q. So we've shown it. So to show that two statements are logically equivalent, we're using the truth table right here to show that they both have the same truth values in the truth table. So this is one method that we use to show that two statements are logically equivalent. Of course, there are many more methods that we're going to look at soon. But for now, we're only looking at the truth table to show that two statements are logically equivalent. Easy. After we look at logical equivalence, the next thing is conditional statement. This is my favorite parts of reasoning and logic. And why that is because for conditional statements, right? For conditional statements, it's very nice, right? It's very nice. As you hear the term conditional statement now, it's pretty much, its truth value is going to be dependent upon, now, as you hear condition, so the statement is dependent on a condition in order for the second condition to be true. All right, so here it says P implies Q. This arrow right here means imply. This arrow, P implies Q. So it's the same as reading if P, then Q. P implies Q, or it reads P only if Q, or Q if P. So those are just different ways we read it. All right, so Q occurs if P occurs, Q if P. P implies Q, or so it means if P, then Q should occur. All right, and so here's an example. It says P is I have a red pen, and Q is I will mark the test. So to read this statement, it means if I have a red pen, then I will mark the test. All right, and so now the truth table of a conditional statement, it's not going to be as straightforward as the conditional statement for the connectives, but it's pretty simple. So now this question asks us to show that P implies Q is logically equivalent to not P or Q. So before we can show the logical equivalence part, we need to know what is the truth table for a conditional statement. So now let's look at the truth table for a conditional statement. All right, so here the condition P implies Q, which means if I have a red pen, then I will mark the test. So let's look at how this truth table will be looking. All right. So first we're going to look at just the truth table for the conditional statement. So we have P, we have Q, and we have P implies Q. So we have P, we have Q, then we have P implies Q. Now here's how the truth table for this is going to look. So for P, of course, we have true, true, then false, false. True, true, then false, false. Then Q is going to be true, false, true, false. True, false, true, false. Now look how we determine the truth table of a conditional statement. So P implies Q. Remember, this is Q if P. So P is I have a red pen, then I mark the test. So true, true, then I have a red pen and I did mark the test. And so P implies Q must be true because I kept my promise. What was my promise to you? I said if I have a red pen, then I will mark the test. So right here was P is I have a red pen, which is true, so yeah. And Q is I mark the test, which I did. And so P implies Q is true. Now P is I have a red pen and Q is false. I did not mark the test. So listen, I lied to you. I told you that if I have a red pen, I will mark your test. But I did not mark your test. And so P implies Q right here is false. P implies Q right here is false. And the only reason why it is false is because I did not keep my promise. I told you that if I have a red pen, I will mark the test. I had a red pen, but I did not mark the test, so I told you a lie. That is the only time the conditional statement will be false. It is only going to be false when the antecedent is true, but the consequent is false. So the only time it's going to be false, P implies Q, is when the antecedent is true, but the consequent is false. So that means I told you a lie. Now here, I don't have a red pen, but I still mark the test. Now I did not mention that I wouldn't mark the test if I had a red pen. I did not mention nothing about what if I don't have a red pen, and so I did not lie. And so this statement is still true. My condition was if I have a red pen, then I mark the test. If I don't have a red pen and I still mark the test, I did not lie. Think about it this way. If I told you that if you get A on your reasoning and logics exam, then I give you $5,000. Now, if you did not get A, but I still give you $5,000, did I lie? I did not lie. The only time I would lie is if you got A on your test and I did not give you any money. All right, that's the only time I would lie. Think about it. So it's the same way right here for the truth table. So if I did not have a red pen, but I still mark your test, I did not lie. Now, if I did not have a red pen and I did not mark your test, I kept my promise. All right, and because I did not have a red pen, so I did not mark your test, so I did not lie. And so down here it is also true. So the only time it is false is when the antecedent is true, but the consequent is false. That's the only time. All right, easy, soft. All right. Now, so we need to look at the next part of this right here, which is to show that P implies Q is logically equivalent to not P or Q. And so to show that it is logically equivalent to not P or Q, what we're going to show is we just need to verify that the truth result of P implies Q is going to be exactly the same as not P or Q. And so let's continue right here and let's find out what would be the truth table for not P or Q. So right here, we're just attaching not P, then this table will be not P or Q. All right, and so this is not P, and this is then not P or Q. And so not P is going to be false, false, true, true. That's not P. All right, now look at this. Now true, true, the negation of true is false, and the negation of true is false. The negation of false is true, and the negation of false is true. Now what we need now is not P or Q. So we're looking at not P or Q. So these are the two that we're looking at. And so true or false is going to be true. And then false or false is just false. True or true is true. And false or true is true. Now what I want to look at is P implies Q, the result from this column right here. Look at it. It's exactly the same as this right here. And so the result of P implies Q is exactly the result of not P or Q. And so we say that P implies Q is logically equivalent to not P or Q. All right. All right. So these two statements are logically equivalent. Now, before I skip right here, the next thing we're going to be looking at is the derivative of a conditional statement. And so you may wonder, what is the derivative of a conditional statement? What are you talking about, sir? Well, what I am talking about is simple. P, for example, P implies Q is, for example, I have a red pen, then I will mark the test. What if I said, I will mark the test, then I have a red pen? Or what if I said, if I don't have a red pen, then I will not mark the test, right? Now notice that all of these that I'm saying, it still includes P or Q, but it's just in different order. Like if I said, I will mark the test, then I have a red pen. That is Q implies P. Alright, all of these type of statements, Q implies P, or not P implies not Q, or not Q implies not P. These are different forms of conditional statement that are known as the derivatives of conditional statement. Alright, so a lot of time with the woman we would say, your mommy tell you to go do something, or your daddy tell you to go do something. And you say, mommy, but and you did something else, right? And your mommy would say, I never that me tell you to do. Alright? And you just say, mommy, are the same thing. You hear what you say, are the same thing. So you might have reworded in your head a different way the instruction that was given. Alright? And so, or next time you might say, no, mommy, the opposite that you tell me to do. Those are derivatives of the conditional statement. Yes, which is what we're going to be looking at now. All right, so that's how we can see that mathematics is in everything. Mathematics is real life. Pure mathematics is the best thing that you'll ever do. All right, so now let's look at the derivatives of these conditional statements. So for example, right here we have, again, P is I have a red pen, and Q is I will mark the test. The conditional statement is P implies Q. It would be if I have a red pen, then I will mark the test. Now, the converse is if I will mark the test, then I have a red pen. That's the converse. If I have a red pen, then I will mark the test. And then the inverse, ouch. Then the inverse right here is if I don't have a red pen, then I will not mark the test. The inverse is given by not P implies not Q. Then the contrapositive is given by if I will not mark the test, then I don't have a red pen. Now the summary of the results are that the conditional is equal to the contrapositive and the converse is logically equivalent to the inverse. Now we are going to justify this using the truth table, but let's just make sense of it in terms of words in real life. Now look at the conditional. If I have a red pen, then I will mark the text, right? If I have a red pen, then I will mark the text. So if I tell you, if I will not mark the red test, then if I will not mark the test, then I don't have a red pen. That is the same thing, you know. Think about it. I have a red pen. If I have a red pen, then I mark the test. Or I can say, if I don't mark the test, then I do not have a red pen. It's the same thing I just said, but I just reword or just restructure my words. So in English language, we say paraphrasing. Alright, and so the conditional is equal to the contrapositive. Now if I tell you, if I will mark the test, then I have a red pen. And I say, if I don't have a red pen, then I will not mark the test. The two of them is the same thing. Right? Same thing, but I just again paraphrase. Alright, so now let's look at the truth table to justify these results. Because in mathematics, we always want to verify our results. If you don't verify your results, then how can you know if the statement is true? So let's write it down. Alright, so let's verify these results. So, first thing, we're going to draw our table. We're going to draw our table. That should be fine. We draw our line. So we're going to need P. So that part is for P. Then we're going to need Q. Then we're going to need not P. Then we're going to need not Q. Then we're going to need P implies Q. Then we're going to need Q implies P. Then we're going to need not P implies not Q, then not Q implies not P. Alright, so that takes care of everything. So let's go ahead and fill out this table now. So we have P, we have Q, we have not P, we have not Q, then we have P implies Q, then we have Q implies P. After Q implies P, then we have not P implies not Q. Then we have not Q implies not P. Not Q implies not P. Alright. Now again, P is going to be true, true, false, false. So it's true, true, false, false. Then Q is going to be true, false, true, false. True, false, true, false. So then not P is going to be false, false, true, true, false, false, true, true. Then not Q is going to be true, false. Wait, the negation of Q, so we're negating right here. My apologies. So we're negating Q, so it is false, true, false, true. So that's what we have. So the negation of true is false, negation of false is true, then the negation of true is false, and then the negation of false is true. And so the next thing we have right here is P implies Q. P implies Q. And so P implies Q right here is, remember, when did we say P implies Q is false? It is only false when the antecedent is true but the consequent is false. So we're looking when the antecedent is true but the consequent is false. So when I tell you a lie, so we're looking for when I tell you a lie. So P implies Q. So P is true and Q is true, then P implies Q is true. Now if P is true and Q is false, then I told you a lie. And so this is the only time it's going to be false. So this one is false, then true, then true. Now Q implies P. Q implies P. So Q implies P is whenever Q is true but P is false, then I tell you a lie. So Q is true and P is true, then this is true. Q is false and P is true, then this is true. Now when Q is true but P is false, then I told you a lie, because I said if this is true, then this must be true. But here it is false, so I told you a lie. I said if Q is true and P is false, then right here is where Q implies P is false. Now the last one is going to be true. Now not P implies not Q. Now whenever not P is true but not Q is false, that's the only place where not P implies not Q is going to be false. So right here, not P is true and not Q is false. This is the only place where it's going to be false. Everywhere else is true. Alright? Now right here, not Q implies not P. Whenever not Q is true but not P is false, that's the only place where it's going to be false. So not Q is true but not P is false. This is the only place where it's going to be false. And so this is true, true, true. Now let's compare what we see from the columns in the truth table now. P implies Q has the same thing or the same truth values as not Q implies not P. We have true, false, true, true. We have true, false, true, true. And likewise, we have the same thing for right here. We have Q implies P and the not P implies not Q. And so the conditional statement is logically equivalent to the contrapositive and the converse is logically equivalent to the inverse. All right, and these are the derivatives of the conditional statement. All right, nice and easy. Now, let's have a look now at the negation of a conditional statement, which is very important, right? Negation of conditional statement. Now, the negation of a conditional statement is this. So, remember, we showed that P implies Q is logically equivalent to not P or Q. Let's go back to it. Right here, we show that P implies Q is logically equivalent to not P or Q. And so why I'm telling you that is, therefore, the negation now of P implies Q is going to be the negation of not P or Q. Alright, and so the negation of P implies Q is P and not Q. So you have to remember this, the negation of P implies Q is P and not Q. Now, we're going to show that. Alright, we're going to show it using the truth table. So the negation of P implies Q is P and not Q. So let's show that right now. So first thing, we draw our table. So we have P, then we have Q, so we have P, then we have Q, then we have P implies Q, then we have the negation of P implies Q, and so we're going to need one more table. That table is going to be for P and not Q. So we're going to need not Q, then we're going to need P and not Q. So this should be it. Yes, this should be enough. So that's fine. So right here, we're going to have P, then we're going to have Q, then we're going to have P implies Q. Then after we have P implies Q, we're going to have the negation of P implies Q. After we have the negation of P implies Q, then what we're going to have is we need not Q, then we need P and not Q. P and not Q. And so for P, it is true, true, false, false, true, true, false, false. Then for Q, we're going to have true, false, true, false, true, false, true, false. And so P implies Q is going to be, P implies Q is going to be, the only time P implies Q is false, the only time it is false is when P is true and Q is false. So whenever the antecedent is true but the consequent is false, that's the only time P implies Q is false. And so this is the only time P implies Q is false. And so everywhere else is true. Then the negation of this column is just the negation of right here. So the negation of P implies Q is false, true, false, true. And so the negation of Q is negation of true is false, negation of false is true, negation of true is false, the negation of false is true. Then we're going to need P and not Q. P and not Q is we're looking at these two columns. And so true and false is false. Then true and true is true. Then false and false is false. and then false and true is false. And so what we can clearly deduce is that the result or the truth column for the negation of P implies Q is the same as P and the not Q. And so we say that the negation of P implies Q is logically equivalent to P and not Q. So what does this tell us? What this tells us then is, let's look at it in terms of words, right? You'll get words for your example. So we say let P be I have a red pen and Q is I will mark the test. So P implies Q will be if I have a red pen, then I will mark the test. And so the negation of P implies Q, it is logically equivalent to P and not Q. And so negation of this statement will be I have a red pen and I will not mark the test. So that will be the negation, which is pretty much the opposite of the sentence. So if I say if I have a red pen, then I will mark the test. The opposite or the negation of that statement is I have a red pen and I will not mark the test. So I'm just telling you point blank period, I'm not marking the test if I have a red pen. Alright, so I have a red pen and I will not mark the test. That is the negation of P implies Q in this example. Alright, so we've just looked at the negation of a conditional statement, and now we're going to look at what is known as a biconditional statement. Alright, so let's look at that now. So a biconditional statement, this is just P, it's just the conjunction of P implies Q and Q implies P. So both of them have to occur, and it is given by this symbol right here. So the biconditional statement is P implies Q and Q implies P, and write it like this. P implies Q and Q implies P. So both of them have to occur. So if P then Q and Q if P. So P if Q and Q if P. Put them together and then we get the biconditional statement. So now let's look at the truth table for the biconditional statement. The truth table for the biconditional statement is just the conjunction of P implies Q and Q implies P. So let's write it down. We have P, we have Q, we have P implies Q, then we have Q implies P, then we're going to have the biconditional statement P implies Q and Q implies P, where this is just the conjunction of these two. Alright? So here it is, P implies Q and Q implies P is logically equivalent to P implies Q and Q implies P. So let's write down the truth results for this now. And so P is true, true, false, false. And then Q is true, false, true, false. Then P implies Q right here is going to be, the only time P implies Q is false is when P is Q but true is false. So that is false, and so right here is true, and here is true, then here is true. Now Q implies P. Q implies P is false when Q is true but P is false. So Q is true but P is false is right here. So this is where we get false. And so right here is true, right here is true, and right here is true. Then now to get P implies Q, or to get this now, we're going to be looking at both this and this. And we need a conjunction. So true and true is true. False and true is false. True and false is false. And then true and true is true. And so this column now represents the truth result or the truth table of a biconditional statement. Alright, so the truth table for This right here, the biconditional statement of P and Q is true, false, false, true. Alright, so some persons might go ahead and memorize this truth table. Nothing is wrong with that. The next thing we're going to look at is a truth table for the negation of this biconditional statement. Right away, by looking at it, we know that the negation is going to be false, true, true, false. Right away, we're going to see that, right? Alright, but of course, logical equivalence come in. And so because logical equivalence come in, we're also going to find, or we're also going to see some other ways of expressing the negation of this biconditional statement. So let's have a look at it. Alright, so supposed to look at that now, the negation of this biconditional statement. Alright, now I'm going to tell you this. The negation of the biconditional statement, so let's type it. The negation of the biconditional statement. So the negation of the biconditional statement is represented this way, the negation of P and Q, right? That's how we write the negation of the biconditional statement. Now I am telling you that this is logically equivalent to the negation of P implies Q both ways, and it's also logically equivalent to P implies not Q. So that's how we find the negation of the biconditional statement. Now, plenty of time you'll get a test and they'll ask you to prove that the negation of the biconditional statement is also logically equivalent to these two statements. So how would you do that using the truth table? Let's go ahead and do that. Alright, so let's go ahead and do that. So let's get a table right here. So we're going to need P, we're going to need Q, we're going to need not P, we're going to need not Q, then we're going to have the biconditional statement of P and Q. We're going to need the biconditional statement of not P and Q. We're going to have the final biconditional statement of P and not Q. So let's put those down. So right here, we have P, Q, we have not P, we have not Q, then we have the biconditional statement of P and Q, then we have the biconditional statement of P, not P and Q, and then we have P with the biconditional symbol, then not Q. Easy stuff. Yes. So P is, we have true, true, false, false. P is true, true, false, false. Then Q is false, true. Well, we can write false, true, but I like to write true first, then false. So let's write true, false, true, false. And then we want not P, and not P is going to be false. Then the negation of true again is false. The negation of false is true. Negation of false is true. Then not Q is going to be negation of Q, which is false, true, false, then true. And then P implies Q, the biconditional statement. Remember, we just looked at the truth table where it is true, false, false, then true. Right? And so the biconditional statement, it is true whenever both P and Q are true and both P and Q is false. So look at it again. I'm going to say it one more time. The biconditional statement is true whenever both P and Q is true or both P and Q is false. That's when the biconditional statement is true. All right? And this result we generated from around here. So remember, we generated it from around, from right here. We generated it right here. All right? So we generated it right here. True, false, false, true. And so again, as we said, whenever both P and Q is true, then the biconditional statement is true. Or whenever both P and Q is false, then the biconditional statement is also true. All right. So let's go back right here now. So the not P and the Q. So whenever not P is true, this is not P. Whenever not P is true and Q is true, then right here is where we're going to have true. Whenever not P is false and Q is false, we're going to have true. All right. Now right here is whenever not P, so right here is then going to be false and right here is going to be false. Now right here now, whenever P is true and the not Q is true, then it will be true. So whenever P is true, and the not Q is true, so it's right here, then the result is true. And whenever P is false and not Q is false, then it is true. Otherwise it is false. Now look at this now. If I were to draw a table for the results of what is the negation of the biconditional statement, I would be negating this column. And so the negation of this column right here, so we're going to negate this column. So we're going to negate P, the biconditional statement of P and Q. So if we're finding negation of that, it's going to be the negation of true, which is false, then the negation of false, which is true, the negation of false, which is true, and the negation of true, which is false. So what can I conclude? Clearly, I can conclude that the negation of the biconditional statement, it is the same right here, and it's also the same right here. And so this statement above represents the truth table of the negation of the biconditional statement, and it justifies this statement of the top is true. All right. Now the next thing we're going to be looking at is tautology and contradiction. Now what are tautologies? Tautologies are statements that are always true. These are statements that is always true. And contradictions are statements that are always false. So example is if I say I am inside or I am outside. Now that is a tautology because it's either I'm inside or I'm outside. If I'm inside, then the statement is true. If I am outside, then the statement is true. And so the statement in that case is always true. I'm never telling a lie. That's a tautology. But if I tell you that I am inside and I am outside, then clearly I'm lying. So a lot of times people contradict ourselves when we're talking on the phone and we say, somebody call and say, which part are you there? And you say, I left out already. I just get a taxi. So you pretty much just say, I am outside. But then 5 minutes later, the person call you back and say, me there which part the taxi stand there, or me reach, which part you there? And you say, I'm just about to leave out. So you pretty much just say, I am inside. But you cannot be inside and outside at the same time. That's a lie. So that's a contradiction. Alright? And so that's just a practical example of how we use contradiction in real life. We always contradict ourselves as humans. We tell some simple lies like that. All right, and those are called contradictions. All right, so let's look at it here. So a tautology is a proposition that is always true. Example, P or not P. And a contradiction is a proposition that is always false. So let's look at the truth table for the tautology. So if we have P, not P, then we have P or not P. This is how it looks. So we have P, so P is true or false because it's one variable. And so not P is going to be false, then true. And so true or false is true, and then false or true is true. And so this is clearly a tautology. So that's one. This one is a tautology. Now the second one, contradiction, the result is always going to be false. So let's look at it. We have P, then we have not P, then we have P and not P. P and not P. And so P and not P, P is going to be true, and or it's going to be false. Then we have false, then true. And so right here we have P and not P. So we have true and false. True and false is false, and false and true is false. And so the result column is always false, and so it is a contradiction. All right. Now the next thing that we're going to be looking at is known as De Morgan's Law. De Morgan's Law. Nice. And so De Morgan's Law states that the negation of and is or, and the negation of and is or, and the negation of or is and. So for example, let's go back to this. We said that the negation of P implies Q is P and not Q. But if we substitute what's for P implies Q, remember we proved that P implies Q is logically equivalent to the negate, is logically equivalent to not P or Q. We showed that, right? So go back to where we looked at logical equivalence. We showed that P implies Q is the same as not P or Q. And so if you replace P implies Q with not P or Q, right, then you get that we have that the negation now of the negation of not P or Q is the same as P and not Q. Alright? Furthermore, we looked at that the negation of P and Q is logically equivalent to the negation of P or the negation of Q. So to do negation, what we do is the negation of and is or, so you have to remember it, the negation of and is logically equivalent to or, and the negation of or is logically equivalent to and. Alright, easy. So the negation of P and Q, you're writing that down. Then the negation of P and Q is the negation of P or the negation of Q. This is going to be very critical, all right, when we're doing a lot of questions. We have to know how to do this, all right? So here we have it, the negation of P and Q is the negation of P or the negation of Q. All right, nice. Now the next thing that we're going to look at is laws of algebra of proportion. What does law of algebra of proportion mean? Now, instead of using a truth table, we can verify everything in reasoning and logics using algebra. And this algebra is known as algebra of proportions. So think about it. This is mathematics. Of course, we have to do some form of algebra. All right? And to do this algebra of proportion, we have to use some laws, right? Some laws are going to come into play. Alright, these law, the first one is the idempotent law. Where we say P and P right here. P and P is logically equivalent to P, and P or P is equivalent to P, which makes sense. P or P must be equal to P, right? Must be equal to P, and P or P and P must be equivalent to P. If I imagine me say I am outside and I am outside, then that must mean I am outside. Or I say I am outside or I am outside, then I am just outside. So that's the first one known as the idempotent law. Then we have the associative law, where we have P and the Q and the R. That's the same as P and Q and R. So imagine we have 1 plus 3, 1 plus 2 plus 3. 1 plus 2 plus 3 is 1 plus 2, which give it 3, then we get 3 plus 3 is 6. Now 1 plus 2 plus 3 can be written as 1 plus 2 plus 3, and 2 plus 3 is 5, and then 1 plus 5 is 6. They're both equal to 6. So it don't matter which part we add first, right? But we just know that P and Q and R, we can have the P and the Q first, then and R, or we can have the P and the Q and R first. And the same thing if it was a OR. Then the next thing is commutative law. P and Q is the same as Q and P. So P and Q is the same as Q and P. And P or Q is the same as Q or P. That's commutative law. Then you have distributive law, which is P and Q or R. And so the and distributes over the or. And so it becomes P and Q or R. So think about it like addition right here. If I did tell you have A times B plus C, how would you work this out? A times B plus C. Then you would get, this would be equal to A times B plus A times C, right? And so likewise for the distributive law, if you have P and Q or R, it's going to be P and Q or P and R. Likewise, if you have P or Q and R, it's going to be P or Q and P or R. So that's the distributive law. Then you have what's known as the identity law, which tell you that P and true is P. Think about it. P and true is P, because if P is false, false and true is false, and so it's still P. If P is true, then true and true is true. And so P and true is P. Then P or false is P. Because if P is true, true or false is true. So the result is still P. If P is false, then false or false is false. And so the result is still P. Now P and false is false. Because anything on false is false. Alright? Because and mean both of them have to be true. So once you have a false in it already, then the result is false. Now P or true is true. Anything or true is true. Then involution law, which tells us that the negation of not P is just P. Because if I say I am not,